So there are three main components to the data preservation problem. Technological obsolescence, the continual evolution of programming languages and applications. The second is unattended fixity, the fact that we really don't have reliable storage that will keep large volumes of research data for multiple years. And the third is self-description. We're still grappling with developing metadata to effectively describe research data such that it makes sense and we can come back to it without having to write huge documents for future users to be able to find their way around it without forensic activity, forensic effort. Repositories are basically software applications. They're embedded in programming languages and operating systems, as well as having APIs to things like library discovery protocols. And they use other major applications such as databases and search engines. They're subject to the evolution of all of these individual components because they're developed by different groups worldwide without any coordination with respect to any single application such as a repository. So the way in which technology evolves creates serial obsolescence. It's not possible to design a large software system and maintain it with a window of any more than a couple of years, because the fundamental components that it uses in its construction are going to evolve beyond a point at which you can alter it and upgrade it without cyclic major rewrites. So the second thing is fixity of research data at rest. When it's operating, fixity isn't an issue. The most widespread storage at the moment is the good old disk drive. And these things will operate for a couple of years. They are precision machines, and they now store tens of terabytes. But after a couple of years, they need to be replaced. The whole thing needs to be thrown away, and either direct replacements or the latest, slightly bigger, slightly faster disks need to replace them, which is, of course, a major waste. The disk has a huge amount of mathematics and electronics which allows it to retrieve information reliably regardless of imperfections in the underlying magnetic medium. It's got a lot of fault detection and correction. Semiconductor storage, SSDs, solid-state disks, are basically memory chips. And these will retain information while they're turned off. And again, while they're operating, while they're powered, they are extremely reliable and will give longer-term service than disks because there are no moving parts. But they're not designed to provide reliable storage on the shelf. We have magnetic tapes, LTO, for example, the tape cartridges, have a shelf life of a couple of decades. They are slower and they're relatively expensive. They are not as expensive as a disk drive, but they're still an investment if you have thousands of them. And actually copying them to new tapes after a couple of decades is a major burden. The problem is that we have no reliable solution for storing large amounts of data for long periods. The third major area of volatility is self-description. So a good old photograph means something to subsequent generations because someone probably wrote on the back who was in the shot, where and when it was taken. Large data sets, such as you might get off of giant apparatus, need the same sort of description. We need to understand the circumstances in which the experiment, whatever it was conducted, what the data set means, what the settings of this enormous complicated apparatus were. The analysis preservation that gives us the geography in which to locate the data and make sense of it without guesswork and forensic excavation in subsequent decades is crucial. There are really no formalizations for this metadata. With simple things like images, it's relatively straightforward in a couple of lines to describe where the picture was taken and what camera the lens was attached to. When it comes to complicated data sets, say from wind turbines, there are many variables, and it may be necessary to look through terabytes of numbers in order to find something of interest. And if the metadata describes that this was a particularly exceptional day and we're looking at a data set which should contain interesting turbulence information, then it saves future researchers analyzing terabytes or petabytes of data in order to find something that they don't have a precise knowledge of. So self-description of the data that we preserve, being able to make sense of what we're looking at in another epoch, is one of the main challenges.